So it's great having Jason from MSSL. Obviously, needs little introduction to this forum, but I should nevertheless mention he's a professor of astrostatistics and astroinformatics. He's also co-director of research at the CDT of Data Intensive Science, and many of the students have obviously met him through this very successful machine learning course that he has initiated, which we luckily recorded pre-COVID, and is now also being used in a collaboration with Jordan. So Jason's, course is now kind of being used worldwide. In addition to his academic activities, he is the founder and CEO of a company called kakanova, and we might hear something about it. I know that it was mentioned today in New Scientist. Congratulations, Jason. We Thanks, might ask you about it later, about what New Scientist has said. But before doing all this great work at UCL and in the industry, just to mention that Jason received his PhD at Cambridge, where he was later also a research fellow at Clare College, and this followed by postdoctoral positions at EPFL in Switzerland, and also at the Astrophysics Group at PNA. His research really covers many topics, and it's really, he kind of, in many ways, represents very nicely the spirit of the CDT. So, a lot about Bayesian statistics, but applications to various ambitious projects such as Planck, SKA, LSST, Rubin Observatory, and so on, as well as many applications outside astronomy, as we might hear about. So Jason, it's great having you, and please go ahead. See that you already shared your screen. Thank you.
Fantastic. Well, thanks for the very extensive introduction, Offer. But yeah, it's great to have this opportunity today to tell you about some of the research that I've been doing. So what I'm going to talk about today is focused on geometric deep learning techniques, and in particular, deep learning techniques on the sphere. And this is actually research done within the startup company that Offer mentioned. But these kind of techniques have a lot of potential for use in cosmology and astrophysics as well. And we're starting now to consider applications of them in these areas as well. So I list a number of people who this work is in collaboration with, a couple of whom you might know, so a number of CDT students actually who have done placements at kakanova contributed to various parts of this work as well. So let me get going. I'm just getting over a cold, so please excuse me if I start coughing every now and then. But anyway, so I also have some Mentimeter surveys to do throughout the slides to try and get everyone engaged a little bit. So if you go to Mentimeter, you can either use that QR code there or just go to www.menti.com and enter that code, and then you'll be put, a question will be put to you. So let me just change my screen sharing. If you go there, basically the first question I want to put to everyone is, what do you think is responsible for this deep learning revolution that we've been experiencing lately? So let me just switch my screen sharing, and I can see some answers are starting to come in. Can you all see the other screen now? Hopefully you can see the screen now with the Mentimeter results. Offer, can you give me a thumbs up maybe if you can see that?
I can see your screen.
Do you see the results of the survey? We're starting to get.
I only see the question and some buzzwords.
Yeah, so these buzzwords are words that everyone is entering now.
Okay.
So this word cloud has been prepared. So we've got a lot of thoughts here on what people think is driving the revolution deep learning, one of which is buzzwords. but also things like
Okay.
data, compute power, statistics, hardware, GPU, madness, cloud compute. So,
Okay.
so yeah, a lot of people have got a number of different ideas on what's driving this revolution. I'd say certainly things like hardware, data, statistics. These are all, really important drivers of the revolution we're seeing. But there's one other which I think is often not on people's mind, and I haven't seen entered so far in this word cloud. So let me go back to my slides. And actually, one of these missing factors that I think people often forget is the role of physics in deep learning. And physics actually is heavily integrated into modern deep learning techniques, basically based around principles of symmetry. So let me explain what I mean here and the role of symmetry in deep learning, and in particular, connections to physics. So with both physics and deep learning, we're often trying to consider quite similar types of problems, but approaching it from very different perspectives. So in a sense, in both physics and deep learning, we're somehow trying to model, we're trying to understand the world. In physics, we usually try and model this from first principles with a physical model describing some phenomena. Whereas from deep learning, we usually try and essentially model or learn informative representations of the world, but in both cases to create generative models and to do inference. And both of these approaches are hard, it's very difficult. And so really, there's a lot of potential for these two types of activities to work together. And as Offa's already mentioned, this is a big motivation for the establishment of this CDT as well. What deep learning can learn from physics and what physics can learn from deep learning. And a lot of the work that probably many of you are doing, we're picking up deep learning techniques and we're applying them to solve problems in physics. In this talk, I'm going to focus on the opposite, trying to see how we can integrate ideas from physics into deep learning. But in general, we want to do both of these. And as we'll see, actually, this kind of connection between physics and deep learning, I would suggest, is actually one of the key factors that has driven this deep learning revolution. So it's often said that physics is nothing more than the study of symmetry. So Steven Weinberg, famous Nobel Prize winner who won the Nobel Prize for the unification of the weak in the electromagnetic force, has basically said symmetry is essentially the key to nature's secrets. And our colleagues in particle physics and high energy physics will be, of course, very familiar with this and the role that symmetry plays in high energy physics. So let me just briefly discuss what I mean by symmetry. The symmetry that, typically people would think about is a symmetry of an object. So here we've got a photograph of a lake which is reflected, a mountain which is reflected in a lake. If we flip the photo upside down, it looks pretty similar. So there's some kind of mirror symmetry going on there. Similarly, here's a card. We can rotate this and, after rotating it a certain amount, we get back to what we started with. So here we've rotated by 180 degrees and we get, something that is the same as what we started with. So in these scenarios, people typically think of symmetry of an object. In physics, generally we think of symmetry in a slightly different way. We usually think of a continuous symmetry, and we think of the action on a system of the kind of continuous transformations of these symmetries. So for example, a common type of symmetry we can have is symmetry to a spatial translation. So if we have some physical system here with a kind of cartoon representation being the solar system here, and if we move the system and then consider how it operates, it doesn't change. The laws of physics, in a sense, are the same in different places of the universe as if we were to translate, say, the universe or move through it. Similarly, we very often encounter rotational symmetry, where the laws of a system don't change under rotation of that system. And so another very common symmetry is time translational symmetry, where, again, the laws of physics typically don't change in time. So I want to go to another survey quickly. So let me just move on to the next one, which I guess for this audience, I'm sure everyone will be very common for people, but the next question I'm just going to share now is, have you heard of ideas of conservation of momentum and energy? In many cases, I've been giving a similar talk to this to mathematicians or computer scientists or others. Even, most people, to be honest, I don't think anyone yet has not heard of these concepts. So since, we're very much physicists here, this audience, everyone has heard of these ideas of conservation of momentum and energy. These kind of often what we would think of as fundamental laws of physics. But actually, so let's look into the role between these conservation laws and symmetry. So Emmy Noether was a famous German mathematician in the early 1900s who made considerable contributions to abstract algebra, but also to theoretical physics. And she proved, in fact, that for every continuous symmetry of the universe, there exists a conserved quantity, and also the reverse. So symmetry is really at the heart of physics, and translational symmetry corresponds to the conservation of angular momentum, translational momentum. It's rotational symmetry that corresponds to the conservation of angular momentum, and time translational symmetry corresponds to conservation of energy. So there's this obviously very tight coupling between the symmetries of the universe and these kind of conserved quantities that we're very familiar about. So in a sense, symmetry is really the foundation that underlies, what often we would think of as these fundamental laws of physics, but really they stem from principles of symmetry. So clearly symmetry is absolutely fundamental to physics. So symmetry also plays a significant role in deep learning. So by encoding symmetry into deep learning models, we can, in a sense, capture fundamental properties about the nature of our world. And so this is how these deep learning models are actually able to capture these properties of our world. So I would argue, although it's probably not, it's certainly not the thing that often comes to mind, as we saw before, people think of data and kind of compute power as what's really driven this revolution in deep learning. But actually, I would argue a key factor has really been this idea of encapsulating symmetry into the architectures and models of deep learning approaches, for example, such as convolutional neural nets. So convolutional neural nets really resulted in a step change in performance, kind of with AlexNet in the early 2010s. And this is really because of this convolutional structure of CNNs. They capture the translational symmetry that we know our universe exhibits. And formally, what they actually capture is something called translational equivariance. So I want to just jump again very quickly to another question, and that is, have you heard of, or are you familiar with the notion of equivariance in deep learning models? So while people are answering that, I've got many more slides here today than I'll present, so I can put a bit more emphasis on this kind of background, or I can, or the technical details later. And so I think depending on how people answer these questions, we'll see where to put the emphasis. So it seems like some people are very familiar with equivariance, but only a few really. Most people either don't know about it, aren't familiar with it, or maybe know a little bit, but would like to know more. So let's spend a little bit of time just reviewing this concept of equivariance in machine learning models. I'll just switch my screen sharing back. Excuse me. Okay, so equivariance. So let's define it formally, simply first, and then look at some diagrammatic representations. So here, this equation shows what equivariance means, but really in words, it's just the same as saying if you here consider some kind of transformation of a signal T and some kind of operation A. So A might be a convolution, say, in convolutional neural nets. Basically, if you transform the signal after application of the operator, so like we see on the left, we do the operator, say a convolution first, then we do the translation, that's the same as doing the transformation first, followed by application of the operator for all possible signals. So this is what's called translational equivariance. And so here's a diagrammatic representation. We start with some space X. We can say perform a convolution, map it to Y, and then a translation. So we get a translated version of Y. But as shown in this commutativity diagram, we can also do the translation first, then the operation. And so we'll see in a second why this is actually so important in deep learning. So here, just to show this a bit more concretely, we have an image of a cat's face. Here we've computed some kind of feature map in our deep learning model, and then we've translated it. And that's exactly the same as first translating the cat and then computing the feature map, perhaps through a convolution or something. So why is this important? Well, basically, what we want to do in deep learning models is impose some inductive biases. And in particular, one that is usually imposed is this idea of equivariance to symmetry transformations, because this then allows the model to be learned in a much more principled and effective manner. We're basically putting this bias into the model that's capturing some fundamental physical properties of the generative process. So certainly for images and computer vision type applications. So by encoding this notion of equivariance to translations, it essentially means that a pattern need only be learned once in a machine learning model, rather than having to learn the pattern in all possible different positions. So for example, here on the left, we've got a picture of the cat, and the cat is in the center of the image. On the right image, the cat's now in the top right of the image. Well, obviously it's the same cat, but we want our machine learning model to appreciate that and not have to learn a cat in the center, a cat in the top right, a cat in the top left, a cat everywhere. The model just learns a cat, and then it can recognize that cat wherever it may be. And so that's really what this translational equivariance that is encoded in these models allows them to do. So it means they can then be trained in a much more principled and efficient manner. Okay, so that's basically just a kind of review on these ideas of equivariance. I'm going to now move on to spherical CNNs and discuss, I'll just check how we're going for time, good, and discuss why we need CNNs for spherical data, which, as you might be aware, comes up a lot in cosmology and astrophysics. So data on the sphere is, in fact, prevalent. So to apply deep learning to these types of data, we need to encode the symmetries of the sphere, which is basically symmetries around rotation. So it's very different to the planar setting for standard images. So here I just show a selection of applications where we get data on the sphere. Actually, it comes up in many applications where it's maybe obvious, say looking at planetary science, looking at the Earth as a whole. You can model the planet quite accurately by a sphere and consider data defined on the surface of that sphere. In astrophysics and cosmology, it comes up a lot as we look out on the celestial sphere. But actually it comes up in many areas where you might not realize it. So for example, in medical imaging and diffusion medical imaging, where you're trying to map the diffusion of water molecules in the brain to trace, say, the white matter fibers in the brain, again, you get these spherical data sets and inverse problems that you need to solve. So this types of data actually comes up all over the place. We'll see an example later from molecular chemistry as well. So two particular areas that I'm very interested in, obviously, is cosmology. The cosmic microwave background is the kind of canonical observation of spherical data, if you like. We look out over the celestial sphere. We essentially observe an image on the sphere that we want to analyze to learn more about our understanding of cosmology and the processes that went on in the very early universe. Actually, we get very similar types of data in computer graphics and virtual reality. If we consider light fields, or what is typically called 360 photos or panoramic images, again, it's really just an image defined on the sphere. So we want to be able to apply deep learning techniques to these types of data sets. So this, right, I kind of mentioned already why this is the case, but we can't just apply Euclidean deep learning approaches. Of course, you could think of unrolling the sphere to a plane like we do when making a map of the Earth, but this introduces distortions. So if you look at the the globe on the left, Greenland here is relatively small, whereas on the projected image on the right, it's very large. It's about the size of Africa. But in practice, Greenland on the left, you can see is 10 times smaller than Africa. So doing these kind of projections introduces distortions, and basically also breaks the symmetry and geometric properties of the sphere. Of course, we could have considered different types of distortions, but it's actually well known, really from the mathematics area, that there's no projection of the sphere that can preserve both shapes in areas. So formally, that's typically said as there's no conformal area preserving projection of the sphere. It simply does not exist. This has been proven. So it means it's really just impossible to avoid distortions, no matter what type of projection you use. So we want to consider our data on the sphere. We want to capture this notion of rotational equivariance. So we want to be equivariant to rotations now, and that's really the analog of translations for planar images. We want to be able to rotate images and capture that rotational equivariance, those symmetry properties in CNNs developed particularly for spherical data. So you simply, again, as I mentioned before, we get distortions if we were to consider planar signals. Also, you cannot capture rotational equivariance if you were to just project spherical maps to the plane and use planar CNNs. Translational equivariance, which is captured in planar CNNs, is not the same as the rotational equivariance. So here we see an example where we're looking just at South America. We rotate it to the South Pole. Well, it's, if you look at the planar projection, there's no way you can translate South America when it's in the center and get something that looks like the one on the right, because it's all spread around the South Pole. Another approach that you might have heard about is something called graph-based deep learning approaches. And in these settings, you construct a graph representation of your data. So one could imagine constructing a graph representation of spherical data and doing graph CNNs to analyze that. But again, that just gives you a discrete approximation. You cannot actually, in these approaches, fully capture the symmetries and geometric properties of the sphere. So you cannot capture rotational equivariance with that approach either. So this leads us to ensure where we need to construct CNNs natively on the sphere. So obviously for data, we're going to need to discretize the sphere, but discretizing the sphere actually is not trivial. And it's well known that actually there's no regular discretization of the sphere. It's quite different to, say, discretizing the plane. So you can't discretize the sphere in such a way that if you were to rotate it, the samples would line up. So here we've got some sampling of the sphere, a rotated sampling, and if we put them on top of each other, clearly the samples don't line up. So that means actually, because we can't, because our sampling patterns, again, not invariant to rotations, it's not possible to strictly capture this idea of rotational equivariance with a discretized representation of the sphere. So that leads us to consider harmonic representations. So we basically consider Fourier representations, and because the sphere is a compact manifold, because of the symmetry properties of the sphere, it means the Fourier space is discrete. So from a discrete Fourier space, we can actually capture all the underlying continuous representations and symmetries of the sphere. So spherical CNNs can be constructed in this manner, basically constructing convolutions on the sphere, and then your typical kind of pointwise nonlinear activation functions. So, basically the analog of what you would do in a Euclidean CNN, but you replace your convolutions with spherical convolutions. I should mention just in passing that other discrete kind of real space constructions of spherical CNNs have been considered. I list a couple of references there. But again, because these are discretized versions in the kind of spatial domain, in the real pixel space, if you like, they cannot capture this rotational equivariance. And some of these are really, nothing more than doing graph CNNs for spherical data. So for the remainder of this talk, I'm going to focus on CNNs that are natively defined in the on the sphere through this connection with the harmonic representation, where you can perfectly capture this equivariance, this rotational equivariance. So I've going to move on to some technical details, but I think I'm going to gloss over the details here. So I've got a few slides coming out that I'll maybe skip some of the details. I think I really just want to give you a flavor for how these techniques have been developed and what they're built on, rather than really going through all the specifics. So I'm going to kind of gloss over these next few slides, and then we'll probably put a bit more focus on some examples and some benchmark problems that we've considered that I'll discuss at the end. So let me at least give you a kind of flavor of these technical details, if not all the details themselves. So of course, we're going to be interested in signals on the sphere. This slide is really just to set the notation. Excuse me. So the sphere we represent with coordinates theta, phi, spherical coordinates, obviously. Because we're considering rotations, we need a parameterization of that. Well, rotations are represented by what's called the rotation group, the special orthogonal group of dimension 3, so SO3, and that we typically represent with coordinates alpha, beta, gamma, so the typical Euler angles that can capture 3D rotations. So we can rotate signals in the spherical domain using these ideas of rotations. Basically it's the complete analog of what you would do to translate a Euclidean signal. You basically, to rotate a function f on the sphere, you basically look up where the inverse rotation maps you to on the original function. And this way now you can rotate functions. As I mentioned, we need some notion of convolution on the sphere. I'm not going to go through this equation in much detail, but actually you can see it's very similar to a standard kind of convolution, say in Euclidean domain. You essentially have some filter that you here rotate, and then you take the product of that with your function and essentially sum up over the whole sphere. That's essentially what this equation is saying. So here's a diagrammatic representation that we have some function f, we have a filter that's being rotated and moving around, we're taking the product and summing up, and that's giving us the convolved map on the right. So this is essentially how we do convolution on the sphere, which is used prevalently in modeling of telescopes as well for the CMB and wavelet analyses. So this is a very common tool in analyzing spherical data. Because, as I mentioned, there's no regular discretization of the sphere, to compute these things accurately, we actually compute in Fourier space rather than trying to evaluate this integral directly. And that then ensures that we can get in rotationally equivariant representation. So I'm going to kind of skip this slide mostly, but basically, as I was saying, we compute these things in the Fourier space. So the Fourier space on the sphere is just the space of what's called the spherical harmonics. So we're just going to be decomposing our signal into a sum of spherical harmonics with coefficients here f, l, m. And again, we do a similar thing. We end up with functions defined on the rotation group. And so again, we have a similar harmonic representation of these, but where the signals are decomposed into what are called the Wigner or the Wigner D functions, these DLMN. And these will crop up a bit later again as well. But basically, we're just considering the Fourier representation of rotations and of signals on the sphere. So as I mentioned, we want to compute convolutions in harmonic space. Convolutions need rotations. We can also compute the rotations in harmonic space using these Wigner D matrices. The convolution can then also be computed accurately in harmonic space. This is a very kind of generalized representation, but essentially it's a matrix product, either if you're considering the sphere or the rotation group. And I think, as I mentioned already, we do this in harmonic space because that eliminates discretization effects And also we can leverage fast algorithms to compute these things in practice. As I discussed already, with standard CNNs, we want this idea of translational equivariance. Well, now we want rotational equivariance. And it's quite easy to see that a convolution on the sphere also satisfies rotational equivariance. So if we do some convolution of our, say, map of the Earth here with some filter and then rotate it, well, it's exactly the same as rotating the data first, then doing the convolution. So we capture this idea of rotational equivariance. With CNNs, we also need some nonlinear activation functions. And again, if we want our whole network to be rotationally equivariant, well, we need to ensure that these activations are also equivariant. So the standard way these kind of nonlinear activations are done in standard CNNs is through a pointwise nonlinear function. So in fact, we can do the same thing on the sphere, but because of this lack of a regular discretization of the sphere, this is actually not going to be equivariant. Nevertheless, this is, so here's some kind of experimental results just showing that, you know, these kind of approaches, like with the ReLU activation function, here we look at the mean equivariance error. For convolutions, we're getting kind of 10 to the minus 7. This is with floating point precision. So we're basically getting floating point precision. But for these like ReLU pointwise activation functions, the errors are kind of 30, 40%. So, so quite significant. Nevertheless, these types of approaches have been used and actually worked, you know, reasonably well. So these approaches taken in some other papers in the literature by Cohen and Estevez. So yeah, I mean, some very nice works there constructing CNNs on these type of approaches. They don't get perfect equivariance, but nevertheless, empirically, these approaches still do pretty well. So what I'm going to come on to now is different ways of doing these activation functions, nonlinear activation functions, in a way that allows us to capture perfect equivariance. So I've got one more question here, which is basically how familiar are people with these ideas of group theory? Who's heard of group theory or not? Let me just show you the results coming in. So, you know, someone loves group theory, and some people agree that beauty is symmetry is group theory. You know, a lot of people know a little bit about group theory, but not a lot, and some not so much. So basically, let me just switch my sharing back. Yeah, so basically group theory is really nothing more than the kind of mathematical study of symmetry. So it's the mathematical machinery that we need to study symmetry. And because we're concerned with rotational symmetry, this is the kind of mathematical machinery we need for these types of methods. So as I mentioned, we're concerned with rotational symmetry. Actually, we're going to leverage the mathematics of quantum mechanics and angular momentum quantum mechanics. So again, you know, this kind of links in with, you know, how physics really can be integrated quite tightly into deep learning approaches. So I'm going to skip the details of the next section. So I'm going to cover this very quickly and then move on to some examples. But basically, yeah, we're leveraging a lot of ideas, and I mean, clearly the problem is different, but the kind of mathematical machinery is very similar to what physics will be familiar with, physicists will be familiar with from quantum mechanics. So we actually, so the whole motivation here is to get rid to have something which is perfectly equivariant. Before we had these ReLU operations that had to operate in a discretized representation of the sphere. It's not possible with that approach to recover equivariance. So we need an alternative. So firstly, we're basically going to generalize everything following this approach in this very nice work of Condor, where we generalize signal representations in harmonic space. Like I said, I'm going to cover this really quickly just to give you a flavor. So this captures representations on the sphere and the rotation group, but others as well, because we allow the size of this component to vary essentially. These types of generalized signals can be rotated in the same way as before with these big D Wigner matrices. We can generalize the notion of convolution in harmonic space for these generalized representations. And the main difference here is that we're no longer forcing the filter to occupy the same space as the signal. So it allows a bit more flexibility. Again, because it's otherwise the standard notion of convolution, it's rotationally equivariant. So how do we introduce this nonlinearity in an equivariant manner? Basically, we consider the irreducible representations of the space of rotations, the rotation group SO3, and we leverage the decomposability of the tensor product. This is first applied in neural networks in these kind of seminal works by Thomas and Condor. Basically, we leverage representation theory, which is concerned about the abstract algebraic representations of structure by linear transforms. And so we're going to consider the tensor product of these representation spaces. And it turns out that these Wigner D matrices provide the irreducible group representation of SO3. So basically, we're going to make use of the tensor product representation. This is not irreducible, so we can recover an irreducible representation by a change of basis. This is what's done by what are called the Cleshp-Gordon decomposition, which is really just Cleshp-Gordon coefficients give you a way of this change of basis to give you an irreducible representation. And actually, this is precisely the mathematical machinery that's used to couple angular momentum in quantum mechanics. So that's really where these techniques have really been developed. So now we have these generalized signal representations. We're interested in this kind of representation because this tensor product is something that is nonlinear and rotationally equivariant. So that's the key. So it's a very different type of nonlinear activation function. Everything operates in this generalized harmonic space, but critically, this gives us something that's rotationally equivariant. Yeah, so I'm going to kind of skip this. And so if we do some numerical tests with this type of activation, we see that these mean equivariance errors are again now at floating point accuracy, whereas we're at kind of 30–40% with the ReLU approaches. So this has led us to construct this much more generalized spherical CNN representation, where we kind of stack together linear, nonlinear, and then linear layers, where the nonlinear layers are typically these kind of tensor product type activations. And then you can see these previous works that I was mentioning as special cases in this generalized framework. Yeah, I kind of actually skipped, I guess, maybe in the previous slide, that, yeah, this is work basically presented in this paper I mentioned at the beginning by Cobb et al., which has just been accepted for ICML, the conference on ICLR, on learning representations. So one of the big, large component of this paper is how to do these things efficiently, because computationally this is very demanding. And in fact, previous approaches have been prohibitively costly, really. So again, I'm going to pretty much skip this, but you have a very high computational cost with alternative variants of this. In our recent work, we came out with a number of ways to reduce the computational cost quite significantly. Firstly, developing a channel-wise structure to do this. Also, the use of kind of constrained generalized optimizations convolutions, where we basically split the convolutions into a number of stages. It's kind of similar to depth-wise convolutions in CNNs, at least in motivation. And again, this allows a considerable computational saving. We also look at these tensor product activations and the set that you need to consider for all these computations. And actually, we recover an optimized degree mixing set of reduced size. And we recover this by using a minimum spanning tree. So where we basically weight the edges of this minimum spanning tree by the computational cost. So this gives us a way to minimize these computations. Yeah, so I won't cover that any further. And finally, we also pick up some previous work of mine developing fast ways of doing harmonic transforms on the sphere and the rotation group. So I kind of, oh, and finally, here's a quick plot of some of the savings we get compared to other approaches. For computational costs, we get savings of up to 2 orders of magnitude there, which grows further with higher resolution. And we're getting kind of 30 times saving in the memory requirements as well. So I kind of glossed over the details there, but nevertheless, hopefully that gives you at least a little bit of a flavor of the background of where these developments come from. So for the final part of the talk, for the last couple of minutes, I just want to go through some examples where we've applied these methods. So what's become a really standard kind of canonical benchmark problem now is classifying MNIST digits. MNIST, as you might be aware, is a very standard data set for machine learning. Here, people typically consider MNIST digits on the sphere. So here we've got some examples of that. This is the architecture that we've considered. It's a relatively deep network with a variety of these different kind of generalized layers combined together. So we consider 3 scenarios here. Firstly, we consider, so the NR means non-rotate. And so the first NR means in the test data, we don't rotate it. And in the training data, we don't rotate it. And also in the test data, we don't rotate. So this is basically putting a digit at the center of the sphere. So in a sense, this makes it almost like a planar machine learning problem. So planar CNNs actually can do pretty well in this scenario. But in the next case, what we do is we rotate the digits. And this is where the rotational equivariance now becomes quite important. Planar CNNs don't do too badly here because by doing these rotations, you're effectively using augmentation techniques to learn that you're on the sphere. But if in the training set, you always put your digit at the same place, but in your test set, you rotate it, then planar methods become almost no better than random. There's 10 digits, so it's not really much better than 10% on each digit. Whereas these spherical methods, because of the rotational equivariance that's encoded in them, still do very well. And for these more challenging scenarios, the techniques I just discussed that we developed are basically achieving the state of the art. But many of these techniques work fairly well in this setting. Another problem where you might not think of having spherical data is, say you want to classify a 3D mesh. So you've got a 3D object, you can actually project that onto the sphere and use these spherical AI techniques to classify it. And again, rotational equivariance is very important here because this model is the same no matter what orientation it's in. So you don't want that to affect your classification. Again, we consider that, in fact, the same architecture that we had previously. So this architecture is not really bespoke for any problem. It's just a fairly general architecture that works well in many cases. And again, basically, we recover the kind of state of the art in a number of common metrics considered for this case. And quite critically, our networks are also much more parameter efficient. So here we have 250,000 parameters, where other approaches have 500,000 or up to 1.4 million parameters. So we're also not only winning on many of the performance metrics, but also the efficiency is a lot higher with our approach. A final problem I'll quickly cover is to predict the atomization energy of molecules. And again, there's a lot of spherical symmetry in this problem. And so you can model fairly well each atom in this molecule. You can basically model its spherical potential, essentially. And so again, very similar architecture to before. So this Montavon was the previous state of the art with the RMS about 6. Previous spherical techniques get an RMS for this regression problem of 8 or above, around 8 or above. We actually saw a very substantial improvement in performance with our approaches, getting an RMS of around 3. So yeah, we're very pleased to see that reduction. And at the same time, as I mentioned before, our networks are a lot more efficient, requiring many fewer parameters. So that basically brings me to the end of the talk. I'll just quickly summarize. So basically, encoding equivariance to symmetry transformations is really critical to recover and encode underlying fundamental physical understanding of the generative process. We need deep learning techniques constructed natively on manifolds. We can't just pick up planar methods or graph-based methods. I reviewed very briefly like this general approach to spherical CNNs and this work we had recently, which has just been accepted for ICLR on a generalized framework that's very efficient as well. So, so this is things we've developed recently. We're now looking at many applications of these, starting to collaborate with others at UCL for diffusion, MRI, and also starting to consider cosmological applications of these types of methods as well. I finally just also mentioned that, as I said, this work was research that was really done inside the startup company kakanova. We're actually a very small startup, but we're also hiring. So if you know people who might be interested, do put them in touch with us. And finally, as Offa mentioned at the start, you can actually learn more about how we've been applying these types of techniques in the area of virtual reality in some articles in Towards Data Science and New Scientist. So we had some articles in Towards Data Science recently, more about this connection between physics and machine learning. But as Offa mentioned, just today, actually, we're featured in New Scientist and about how these AI techniques we're developing can be used to basically get rid of cyber sickness. So if you want to read more about kind of applications and uses of these kind of techniques, check out those articles as well. And of course, feel free to share them on social media and let others know about it. So thanks, Offa. Sorry, I realized I went a little over time, but yeah, please let me know if anyone's got any questions.
Yeah. Thank you very much, Jason, for a great talk, taking us all the way from fundamental physics to these applications.